welcome to episode 62 of the Structure and Interpretation of Computer Programmers podcast. I'm Graham Lee, and this episode is the sixth part in a mini-series exploring the NATO software engineering conferences. The episode is sponsored by you, the software engineering community. If you enjoy this podcast, please share the link with your friends and colleagues. In episode 61, the conference was dominated by two issues. First, an attempt to bootstrap a NATO software engineering institute that failed, and that isn't covered in the conference report. And second, a gulf between theoreticians and practitioners, between academia and industry, between computer scientists and software engineers, and between Edgar Dijkstra and anybody else. That last ravine appears again at the outset of section 4 on software flexibility. Alan Perlis starts off trying to make an analogy between a hierarchical design and an onion. The design has multiple layers, each of which has an inner interface, the way that it uses things from the lower layers, and an outer interface, the things that it provides to the upper layers. Dijkstra jumps in to say that the onion is a bad analogy because it's three-dimensional, and a hierarchical design is one-dimensional. He'd prefer if we kept those higher dimensions free to represent other attributes of the design. The report editors split flexibility into two categories: portability, the ability to run software on multiple systems, and adaptability, the ability to keep up with changing requirements. Although it's clear from the report that some attendees think of migrating software between systems as an adaptability problem, the two categories aren't actually disjoint. Perlis was trying to make a point about portability, which is a valid but incomplete definition. That portability is concerned with creating support on new machines sufficient to accept systems transported from old machines. In other words, if you can emulate the facilities or interfaces of the old computer on the new computer, you can run your old software on your new computer. Think of the way that Solaris on Sun 4V hardware, at least until version 10, and I have never used version 11, still supports system calls defined in BSD, so that Sun OS 4 programs that were written for Sun 4M hardware still work. Much of the discussion in the section, though, takes different approaches, the first being a high-level language. As Stephen Warshall of Applied Data Research puts it, a program is descriptions by people of computational processes, and you can communicate that description without having to describe a computer. Describe your solution at sufficient abstraction from the hardware capabilities that it doesn't rely on specific hardware provision, and then provide the support facilities, in other words the language runtime, that allows it to execute on both the original system and on possible future systems. This fits Perlis's onion model. The program in its high-level language is the outer interface of the onion layer, and the language runtime support is the inner interface. The trap is that the more abstract the computational model of the language, the more capable the runtime needs to be to make the program executable. Warshall's solution is to add another layer to the onion. As Kevlin Henney says, any problem in computing is solvable with another layer of indirection, except the problem of having too many layers of indirection. The layer he adds is the virtual machine. Consider the use of software as a device for eliminating representational commitments. To quote him, that layer provides a simulated computer that the high-level program runs on well, that expresses its needs in terms of the facilities the target hardware provides. You lose the ability to fine-tune performance by directly expressing the software in terms of the target system, but you gain a lot in terms of portability. Two problems with this approach are, one, that you can't actually predict the future very well, so an upcoming target system may have facilities you can't use from the virtual machine, or a design that makes the VM highly inefficient. As an example, imagine virtualizing the tape interfaces on some computers, then receiving hardware that has random access storage. Secondly, that the abstractions provided by the high-level language become unrealistic. Here, the example Warshall gives is you might write all programs as though you had infinite memory and then let some automatic device worry entirely about storage strategy and resource strategy. That's actually what we do these days. If you look at the memory allocator in a modern operating system, you'll usually find that the malloc function can't fail and always returns a null pointer to virtual memory. or at least with a 64-bit address space, it takes a long time before it runs out of pointers to give you, which is the only reason that it actually does fail. It's only when the program actually tries to use that memory that the runtime tries to get the kernel to commit some memory to support it. And it's only when the kernel runs out of memory to offer that things start to go sideways. Of course, by relying on high-level languages, you really just kick the problem down the road. Yes, your software is defined in a portable way, but until someone ports the virtual machine or runtime library, it isn't actually portable. You can bootstrap porting something like a compiler by creating a compiler that runs on the computer you already support and generates code for the computer you want to support, and then compiling the compiler for that new computer using the old computer, and then the compiler for the new computer using the new computer. Strachey talks about porting Martin Richards' BCPL compiler, which is written in BCPL with some assembler language, by rewriting the code generation path in Algol, providing a portable means of compiling the compiler. Of interest to retro computing fans is that Martin Richards also wrote the Tripos operating system in BCPL, which became the basis of Commodore's Amiga-DOS after their own in-house project ran into trouble. An alternative approach to abstracting the target of your high-level language is to use macros, so that machine-dependent statements in your program have different values on different target machines. Jerome Feldman and Dijkstra both explore this idea, which evolved into its ultimate form with the GNU Auto Tools, a very complicated macro facility that generates programs to test what values to give the macros, and that many people use without understanding it. They both make the point that what you end up with isn't a portable program, but a software product line, though they don't call it that because it's a 1990s phrase. What you end up with is a family of related programs and a process that selects and creates one instance of that family. Perlis wishes for tools that stop you doing machine-specific things and warn you if you somehow still manage to do it. But John Buxton of Warwick University comes to the Gordian knot of portability in 1969, which is that the support tools, the compilers, assemblers, runtime libraries and so on, that people relied on in the 60s were, for the most part, supplied by the hardware vendors. These are the people least invested in making it easy to port your software to a different computer because you've already bought their computer if you're using their tools. I just want to add a couple of other points from the discussion on flexibility, because while they're small, they're very important. One is that General Electric's Bob Boehmer and conference co-chair Professor Friedrich Bauer both point to the needs to make data portable as well as programs to successfully port a system, with Boehmer lauding the COBOL separation of a program into divisions as a facility that enables portability. Now he would say that as he was one of the creators of COBOL. The algorithms in a COBOL program are defined in a procedure division. The variables, structures and data interfaces are in a data division, and the target machine and configuration are in an environment division. You can use the same data and procedures on different machines, or in different configurations on the same machine, just by changing the environment division, the same procedures with different files by switching the data division, and so on. Bauer's idea is that you need to record the data schema somewhere, either in the program, as COBOL does with its data division, or in the database itself, so that the database becomes self-describing. Another point is that Butler-Lampson takes the point on flexible runtimes a little further by saying that if you have modules with well-defined interfaces, you can wrap those modules in an envelope and reuse them in different contexts without needing to change the module's program. That idea crops up again in the Gang of Four book, where it's called the adapter pattern. This is the advert break. It starts now. This episode is brought to you by me, Graham Lee, but really by you. Chiron Codex is a community of people who are learning how to become better software engineers by adopting AI augmentation in a thoughtful way. We aren't outsourcing our understanding to coding assistants like Claude or Codex, but becoming software engineering centaurs by using AI tools to improve our knowledge and the quality of our work. Join the community over on Patreon to find out about interaction patterns that improve your work with AI coding tools, running LLMs for software development locally, discussions of recent research in the field, and more. If you're a software engineer who's interested in the promise of AI tools, but skeptical about handing your skills over to the computer, this is the community for you. Go to patreon.com/ChironCodex, that's ChironCodex, now for more information and to join. Use the gift link in the show notes to get your first month of insider access completely free. Alternatively, you can show your appreciation by donating at Ko-fi. That's ko-fi.com/ChironCodex, ko-fi.com. Direct support by my audience is the only revenue I get for my work as a software engineer and communicator, so your support really means a lot to me and makes it possible for me to produce this podcast. Thank you so much. That was the advert break. It's over now. Section 5 is on large systems, and we're launched straight in with what has to be the money quote for this episode from J.I. Schwartz of King Systems. I must admit that I have frequently asked myself whether these systems require many people because they are large, or whether they are large because they have many people. Maybe both are true. We saw in the peak eras of Silicon Valley hiring excess, which I define as the dot-com boom that ended in 2001 and the web-scale boom that ended in 2023, that companies would hire software engineers just to try to stop their competitors from hiring them, and would then need to find projects for them, and would then grow systems in weird ways with weird personnel needs that they could then cut when they needed to reduce headcount without materially affecting their outcome. So maybe this is a kind of spatial variant of Parkinson's law, where the work expands to fit the headcount available. After giving an example of a large project, the NASA Apollo mission, which featured at least 600 people from IBM with 300 programmers, J.D. Aaron describes their experience with super programmer projects. Fred Brooks also writes about this in 1971's Mythical Man Month under the name Chief Programmer Team. In both cases, the super or chief programmer is Harlan B. Mills, a man who, with 36 PL1 manuals open on his desk, tried to replicate in 6 months a 30-person-year Army of Ants project. He failed at that, but still completed the project in a small number of years. However, IBM were doing what they could to shield Mills from their customer, meaning that his more efficient project turned out to be worse at doing what the customer actually wanted. As Brooks presents it, the chief programmer is a highly capable expert in total charge of the project, with a few support staff to delegate some of the work to, including a full-time project wrangler, a support toolsmith, and a programming language expert. These teams can indeed get significant work done with fewer resources than large teams, but there are multiple factors at play. Is it the Brooks' Law issue, that there are fewer people so less time spent on communication? This is the bet behind the two-pizza team, which doesn't mention chief programmers, just small teams. Is it that these chief programmers are genuine 10x programmers, and that the 300-person projects are full of NNPPs, net negative producing programmers? Or is it that when someone comes along and says, I bet I could do that in less time than your large team did, they've pre-selected the project as one that they think they can succeed at? This is something that happened over and over again with the various Twitter clones that have come and gone, with one of the loudest being App.net. The team behind App.net proudly announced how quickly they'd got their product off the ground, when it had taken years for Twitter to build the same features. The two differences, of course, were one, that Twitter had to design and validate Twitter, whereas App.net just had to build an implementation of the existing design, and two, Twitter still exists. It's in section 5.2, the sources of problems in large systems, that we find another of the irreconcilable differences between industry and academia. The conference has decided, just as its forerunner did, that large projects are the source of most problems in software, and there are a lot of regular software initiatives that work just fine. So, why did the large projects go wrong? On the one hand, Aaron from IBM says virtually all reasons for failure are essentially management problems. Yes, there are technical problems, but choosing the correct techniques is itself a managerial problem. As Alan Perlis says, putting in his runner-up entry for this episode's money quote, the managers wouldn't know a good technique if it hit them in the face. On the other hand, Tony Hoare says that basically all problems are technical. The reason that large projects fail is that they represent problems humanity doesn't know how to solve, so it was a mistake for the manager to try to solve them without first doing some basic research. There's a bit of presentation from working papers and discussion of the support systems needed for large projects, and the answer is basically an integrated development and project management environment. Version control, programming, filing system, debugger, linter, job submission, time accounting, dependency tracking, and more, all in one database. It's interesting to note that even though IBM developed the environment they describe in this report, called Clearcaster, the first commercial IDE was probably the Rational R1000 workstation for Ada in 1985, unless of course you consider the online programming environment in Dartmouth Basic to count as an IDE. The last section to cover in today's episode is Section 6 on software engineering education. Alan Perlis sets up the discussion with 3 questions. 1. Is there a real distinction between software engineering and computer science? 2. Given that the answer to question 1 is yes, is there a need for education in software engineering as a separate discipline? 3. What form should university courses in software engineering take? It seems like question 3 assumes the answer to question 2 is also yes. So in fact there's only one question here. I think the subsequent discussion mostly focuses on the perceived prestige of different degrees in the US and the broken incentive structure of US academia, with only a little diversion into the question of how to teach software engineering. It turns out that computer science at the doctoral level results in a PhD, which is considered a, and I'm using my scare quote fingers here, proper degree. You do a lot of teaching and a bit of original research to get a PhD in computer science. Now, is it necessarily the case that someone who wants to become qualified in software engineering needs to advance the state of the art? Can't they just learn the practice? That question doesn't quite go unanswered, but the answers do really circle around the issue quite a lot. The problem American academics, at least the ones at the 1969 conference, have with software engineering is that if you graduate an engineering program with a doctorate in engineering in the US, these aren't, using my quote fingers again, proper degrees in the way that a PhD is a proper degree. Feel welcome to email me about this point if you wish, but you shouldn't get angry with me. I'm paraphrasing what's in the report and I don't have an opinion on the status of an American doctorate in engineering. Bob McClure summarises the state thus. Most computer science departments output lone workers with computer science degrees whose career capability is best described as can become faculty at another computer science department and train PhDs in computer science. Universities thrive on their reputation, and their reputation is determined by whether academics think they're any good. So aspirational universities will try to emulate good universities by outputting CS PhDs who can become faculty at CS departments, ideally in good universities. Meanwhile, industry wants a lot of people with bachelors in engineering who can do quite good work, some people with masters in engineering who can do good work, some people with doctorates in engineering who can do very good work or direct the work of those with the bachelors and the masters, and no people with PhDs in computer science who can extend the state of the art but can't work with other people. However, due to the aforementioned degree snobbery, students want PhDs, which universities are happy to help them with to boost their reputation for creating PhDs, because those are the, fingers again, proper degrees. The 4 things we learn about software engineering education in this section are: 1. Practitioners don't read any research. 2. A practitioner who did read the research wouldn't be much of a theoretician, and a theoretician who wrote a program wouldn't be much of a practitioner. That division again. 3. The textbooks aren't worth anything, assuming that they exist at all. Butler Lampson only has time for Knuth's The Art of Computer Programming, and that as an encyclopedia, not as a textbook to teach from. 4. The body of knowledge isn't well defined enough in 1969 for Strachey to believe there's a whole degree's worth of material to teach, which probably also explains why there aren't any good textbooks. That last part probably was true. The IEEE Computer Society didn't even put out a prototype guide to the software engineering body of knowledge until 1998. A question that remained open was whether software engineering in itself was a valid discipline, or whether people also needed to learn something of hardware engineering, in which case they would be more like informaticians or cyberneticians, than software engineers. Clearly, the people in favour of the combined discipline lost. I have an MSc in software engineering. I've also taught on a degree subject. I've linked to the syllabus in the show notes. No hardware in there. Now, the question is, what drove that collective decision that society made? Did software people not want to bother with the details of hardware? Did universities not want to add hardware modules to bloated software courses? Did employers not care whether software people knew about hardware? Did hardware get too complex to teach in a software course? I did a little bit of hardware engineering in my undergraduate degree, which was physics, not computer science or software engineering. We had a little 8-bit processor made out of TTL chips, that's transistor to transistor logic, and we had to extend it by adding a subtract instruction. Interesting, yes, but did it make me a better software engineer? Or for that matter, did it make me a better physicist? All that's left in the 1969 conference report, and therefore in this mini-series on the 2 NATO software engineering conferences, is the collection of working papers. This is more than half of the report's body, but I won't cover the whole thing in detail. In the next episode, I'll share some highlights from those papers. In the meantime, you can leave your thoughts about this episode at the post on sicpers.info or email me grahamlee@acm.org. Thanks so much for listening. Please consider supporting the podcast on Patreon or on Ko-fi. Take care, and we'll talk soon.